Now what we're going to talk about is something that's incredibly important inside of number theory, and that's work with primes. So primes end up becoming really, really important just in the study of numbers and the study of number theory from a mathematical perspective. But from a computer science perspective, basically all of cryptography, all code breaking, all of your security is based upon prime numbers and prime number factorizations. And so consequently, primes and understanding primes are really important for understanding that branch of computer science. So let's start out with this idea of what is a prime. So an integer p greater than 1 is called prime if the only factors of p are 1 and p. And so then a number that is not prime is composite. All right. So if we look at that, like say for example, the smallest prime is 2. All right. 2 equals 1 times 2. All right. And there's no other factors of 2, so 2 is the smallest prime. The number 1 is not a prime number. It's not composite either. It's just, well, it's 1. There you go. Okay. But 2 is 1 times 2. 3 is the next one. 3 equals 1 times 3. Okay. Then after that, we start getting even numbers, and we know that even numbers, okay, so these guys are prime. We know that even numbers are always going to be composite because they're always divisible by 2. So for example, 4 equals 2 times 2, 6 equals 2 times 3, and so on and so on and so forth. Okay. Anything that's divisible by 3 is also composite because it's divisible by 3. So not all odd numbers, for example, 9 is not prime. 9 is in fact composite because it's 3 times 3. Let's talk about like basically some of the most common prime numbers. So the primes, 1 to 100. Okay, and you should basically know what these are. This is just a good thing to know. From a mathematical perspective, we have 2, 3, 5, 7, 11, 13, 17, 19, excuse me, 19, 23, 29, 31, 37, 41, 47, forgot one, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 87, not 87, excuse me, 89, and then 97. So what you'll notice is that bunched up down towards the bottom, 2, 3, 5, 7, even 11, 13, 17, 19, we have, kind of dense packing of primes. But as we increase our values, we end up with fewer and fewer primes. For example, 97 is the only one in the 90s. And that kind of makes sense because as you increase your numbers, it's more and more likely that they're going to be divisible by a number that's smaller than that number. Okay, and so hence our primes become, less and less and less densely packed. They kind of expand out. One of the big results that we get out of that then is this thing called the fundamental theorem of arithmetic. And so you know that if something's called the fundamental theorem of something, that it's pretty important. Like it's hugely, massively, gigantically important, right? There's fundamental theorems of calculus, fundamental theorem of algebra, then there's the fundamental theorem of arithmetic. In some fields, there are more than one fundamental theorem, and I just want to say that that's not right because you can only have one fundamental, right? Like your grammar's off. But in this case, this is our fundamental theorem of arithmetic. And it's basically stating that any number bigger than 1 can be written as a prime or the product of 2 or more primes, right? Basically that we can prime factorize anything, right? And we call the product of n's the prime factorization. So for example, 7 is prime, so we just write it as 7. But like 42 is 2 times 3 times 7. 55 is going to end up being 5 times 11, and 120 is going to end up equaling 2 times 2 times 2 times 3 times 5, which in this case is 2 cubed times 3 times 5. The convention that we're going to write is we're going to write the primes descending, Okay, and we're going to use that instead of some proofs and different things like that. So make sure that you write your primes, ascending. That is the smallest prime at the farthest left, going all the way to the largest prime on the right. Okay, and notice that we generally will write, if we have multiple factors, we're going to write them as a power, like in this case, the 2 cubed. So the next thing we want to talk about is constructing a prime factorization and factor trees. You don't have to use factor trees in order to do your prime factorization, but I do find it to be really, really handy and very productive because what it does is it creates a graphical way of thinking about a prime factorization and actually breaking up a number into its factors. Okay, and we're going to start out with this idea, this theorem that we have, that if n is a composite integer, then n has a prime divisor less than or equal to the square root of n. All right, and what I want to do is I want to just briefly kind of prove this because I think this proof is interesting and it kind of shows us how some prime number proofs are done. Okay, so here's our proof. Okay, suppose that n is a prime number, n is composite. Okay, and let n equal a times b, right? Where a and b are integers, right? And at least one of a or b, at least one of a or b is a prime number. Okay? And what we're going to do is we're going to prove this by contradiction. So suppose that a is greater than the square root of n, and b is also greater than the square root of n. Then ab, right, which equals n, right, n equals ab is going to be greater than, or excuse me, yep, it's going to be greater than root n times root n, which equals n squared. So, or excuse me, root n squared, which equals n. That is a contradiction. So, either a is less than or equal to the square root of n, or b is less than or equal to the square root of n. Since a and b are divisors of n, at least one of the divisors of n is less than root n. Okay, so we're going to use this fact. We're going to use this fact if we ever get stuck. Because sometimes you're going to come up with numbers and it's going to be kind of difficult to figure out whether or not they actually are prime or not. Okay, and you don't want to try every single number, every single value, okay, to see if in fact divides whatever number you're looking at. So this particular fact is actually going to be really kind of handy and important. Okay, so let's construct a prime factor tree or a factor tree for 343 to find its prime factorization. So we've got 343, okay, and I mean I've got a couple of things that I want to think about, all right, and a couple of little facts that we probably want to know. If n is even, n is divisible by 2. Okay, so we've got that. If the digits of n add up to a multiple of 3, then n is divisible by 3. So we're going to use those two facts. See if that's the case. So I take 3, 4, 3. It's not even, so it's not divisible by 3. Okay. Also, if I add 3 plus 3, that's 6 plus 4 is 10. Also not divisible by 3. so consequently it's not divisible by 3. We can also check 5. 5, it's not going to be divisible by 5 because it doesn't end in a 0 or a 5. Okay, so we could check 7. All right, we'll check 7. So I'm going to take 343 divided by 7. Excuse me. 343 divided by 7, and that's equal to 49. Oh, great. Okay, so this ends up being 7, and that's 49. Okay, this is 7 times 7. Now, all three of the numbers at the end of the tree, 7, 7, and 7, are all prime. Okay, all prime. So that tells me that I can actually stop. In a prime factor tree, what we'll do is we'll take a factor of the top number, all right, and divide by that factor, and we'll end up getting the other value, whatever the other value is. If it in fact can be factored, then we'll take 2 of its factors and make the next set of branches of the tree, okay, until we finally end up with the prime factorization. In this case, 343 is going to equal 7 times 7 times 7, which equals 7 cubed. So let's take a look at another example to find the prime factorization of 186. Okay, well, you take 186 and you look at that, that's even. Since it's even, I know it can be divisible by 2, so I'm going to divide by 2, and that in fact is going to give me 2 times 93. Now 93 is 9 plus 3, that's 12. That's divisible by 3, so 93 is also divisible by 3. It's 3 and 31. Now, is 31 prime? Well, let's check. The square root of 31 is actually, it's going to be approximately, right, 4, 5. It's smaller, it's bigger than 5, okay, but smaller than 6, okay? So it's somewhere between 5 and 6. And how I know that is because 5 squared is 25 and 6 squared is 36. So 31 somewhere in between those two. So root 31 is going to be somewhere between those two values, okay? So what I know is that I'm going to have, right, the square root of 31, all my possible prime factors. My possible prime factors are those that are less than or equal to 5, right? 6 is too big, so we got to go less than or equal to 5. 2, no, it's not even. 3, nope, because 3 plus 1 is 4. 5 doesn't end in a 0 or a 5, so 31 is prime. Consequently, 186, its prime factorization is going to equal 2 times 3 times 31. And there's the prime factorization. Notice, once again, all we've got to do here for the prime factor tree is take the top number, whatever number we're trying to factor, we'll divide it through by one number that we happen to know be one of its factors, and then the other branch of the tree is going to be whatever that the quotient is, right? In this case, 93. Then we're going to factor that value, and so on and so forth until we finally end up with all of the ends of our branches are all prime numbers, and that's our prime factorization. The next crucial topic for us is this whole idea of a greatest common divisor. And you're going to see inside of the coming weeks that the greatest common divisor is actually really very important for working inside of number theory, that we use the GCD in a lot of different scenarios. And in fact, that it also allows us to do things like cryptography and code breaking and the like. And so it's really kind of crucial for us to be able to work with the GCD, to know what it is, and have a lot of different ways of finding it. Because when the numbers get really big, it gets really hard to find a greatest common divisor, okay? So let's first start with a definition. So given two integers, the largest number d such that d divides a and d divides b is called the greatest common divisor of a and b and is written as the GCD of ab, all right? So for example, the GCD of 24 and 54, okay? If I think about what are all of my different factors for 24, okay? The factors of 24, okay, are going to be 1, 2, 3, 4, 6, 8, 12, and 24. The factors of 54 are going to be 1, 2, 3, 4, no. 5, no. 6, 9, 18, 27, and finally 54. The greatest common divisor is the biggest one that they have in common, and so the GCD here, if I look here, is going to end up being 6. So my GCD ends up being 6, right? So GCD of 24 and 54 equals 6. Okay. Now, sometimes it's not going to make a lot of sense for us to actually go in and write down all the factors of a particular set of numbers, because that particular set of factors could be really long. We could actually have a really big set of factors, and it could be really kind of difficult to kind of list them all out and then go look for the one that they have in common. So what we want to do is we want to actually go out and find a process that will allow us to find the GCD. And we're going to have a lot of different processes that will help us to do that. The first one that I'm going to do, though, is this one called using a prime factor tree, or using a factor tree to find the GCD. Okay? So the idea here behind using the factor tree to find the GCD is that the factor tree breaks up a number into its prime factorization. Okay? And the GCD is going to be all the prime factors, right, that both numbers have in common. So the largest group that they have in common is going to end up being your greatest common factor, right? Because you're going to see those pieces all factor in the individual number, all right? And so consequently, that's how we use the prime factor tree. We go find, right, what that factorization is, and then we pick the ones that they all have in common, okay? So let's start out, we'll do 180, all right, and then we'll do one for 245. So 180 is 2 times 90, okay, which is 2 times 45, which is 5 times 9, which is 3 times 3, okay? So 180 equals 2 squared times 3 squared times 5, okay? Now 245 is going to be, well, it's not divisible by 2, but it is divisible by 5. So it's going to end up being 5 times, let's use quickly, we'll take 245 and divide it by 5. It's 49. 5 times 49, 7 times 7. And so consequently 245 is equal to 5 times 7 squared. Now, what we're going to look for is the things that they have in common. And if you notice, they both have a 5 in common. And that's it, right? No sevens in 180, and no 2s or 3s in 245. So consequently, the GCD of 180 and 245 equals 5. So what we did was we basically created a prime factor tree in order to find the prime factorization of the two numbers, and then we just compared whatever ones they had in common. Had 245 had like some 2s in it, we would have had to multiply by 2, right? But it didn't. So consequently, no 2s in it. Had 180 had any 7s in it, we would have had to multiply 5 times 7, right? To incorporate in the 7 as a factor of both numbers. Now we want to construct another really important definition, and it's the idea of being relatively prime. So the integers a and b are relatively prime if the GCD of a and b is equal to 1. All right. So basically, if we go out and we find that the greatest common divisor of the two is 1, then what we end up with is we have two relatively prime numbers. They themselves, by themselves, are not prime. It's just they don't share any factors. That's basically the idea. So no sharing of factors. So let's say we want to show that 77 and 36 are relatively prime. Well, 77, if I construct a factor tree, is going to be 7 times 11. Okay, so 77 equals 7 times 11. And 36 is going to end up being 2 and 18, 2 and 9, and then 3 and 3. So 36 equals 2 squared times 3 squared. Notice, right, that they don't share any factors. notice that 77 and 36 do not share factors. So their GCD, their greatest common divisor, okay, so their GCD is 1. And that's probably the most basic way of going out. Not necessarily the easiest way, but that's the most basic way of showing that two numbers are relatively prime. We just basically construct a prime factorization and show that they share no factors. And since they share no factors, that's what makes them relatively prime. Now, if we go out, we've got another definition here. Numbers A1 through AK are pairwise relatively prime if the GCD of AI, AJ are relatively prime for all I, 1 less than or equal to I, less than J, less than N. So basically, if we go through and we compare them all, okay, pairwise, we can see that they don't share any factors. Then what we get is we get relative pairwise relatively prime group. All right, so let's say, for example, we've got 9, 77, and 40. So 9, right, 9 is going to equal 3 squared. 77 is going to equal 7 times 11. And 40 is going to equal 2 cubed, which is 8 times 5. Okay? Now, if you notice, right, 9 and 77 are relatively prime because they don't share any factors. 77 and 40 are relatively prime because they don't share any factors. And 9 and 40 are relatively prime because they don't share any factors. Okay? We compared all the pairs. We compared them pairwise, one against each other. Since, right, 9, 77, and 40 share no factors pairwise, this means 9, 77, and 40 are pairwise relatively prime. We have this definition because sometimes we actually want to look at a whole set of numbers or group of numbers. All right, this is going to come up in later on when we look at something called the Chinese remainder theorem. That we may want to look at a group of numbers or a set of numbers and ask ourselves whether or not they are all relatively prime compared to each other. And if they are, then what we end up with is we end up with things that are pairwise relatively prime, and they have some very special characteristics. So the kind of partner idea to the greatest common divisor is least common multiples. So least common multiple of A and B is the smallest positive integer that is divisible by both A and B. And we're going to denote this integer or this number as the LCM of A and B. So some examples, the LCM of 3 and 4 is 12, right? 12 is divisible by 4, 12 is divisible by 3, and there's no number less than 12 that's divisible by both 3 and 4. The LCM of 20 and 40, on the other hand, is 40, okay? Because 40 divided by 40 is 1, okay? And 40 divided by 20 is 2, and we can't get any smaller than that, right? Okay, that 40 divided by 40 is 1, nothing, right? No number, okay, smaller than 40 is going to be divisible by 40. So 40 is it. On the other hand, we have the LCM of 12 and 20 is 60. Notice that 12 times 20 is not 60, okay? It's some other number. It's in fact 12 times 5 and 20 times 3. So in this case, we don't have like one of the actual values be a multiple, okay? On the other hand, we also don't have the case in which it's two numbers multiplied by each other, okay? So we've basically got these three different scenarios, right? Where you take the two numbers that you're trying to find the LCM for, you multiply them together, that gives you the LCM. Or we might have one of the values actually is the LCM. And then the third case is it's something else going on. So what we want to do is we want to figure out what it is, okay, or what I need to do, okay, in order to find that least common multiple. And we're going to look at those prime factor trees, and we're going to do some work with them in order to find the LCM. So what we're going to do is we're going to use the prime factorization to find the LCM. So let's take, for example, we look at 20, okay? And 20 is going to equal 2 squared times 5, right? 4 times 5, so that's 2 squared times 5. And 21 equals 3 times 7, all right? Now, what I know is that whatever multiple I have has to have all of the factors of my two numbers, okay? In this case of 20 and 21. And the reason why that's the case is that if it is missing one of the factors, then my number isn't going to go evenly into it, okay? The only way that we can have something actually be a multiple of one of my values is if it actually shares all of the factors, okay? Basically, it's like 21 is 3 times 7 times something else, right? 20 is equal to 2 times 2 squared times 5 times something else, right? Say, for example, like 80 is just equal to 2 squared times 5 times 4. And 84 is going to equal 2 squared, is going to equal 3 times 7 times 4. Okay? So notice, not 21, but 84. Notice how in both of these cases, 84 is a multiple of 21, right? And 3 times 7 is incorporated inside of a factorization for it. Inside of 80, 2 squared times 5 is also, it's the prime factorization for 20, and it's also in this factorization for 80 too. And that's going to be the case for all of them, right? So what we need to do is we need to make sure that we have all the factors, right? Okay, in my multiple or my least common multiple that are also inside of that are inside of my original two numbers. Okay, and the smallest one is going to be the one that shares all of those factors and nothing else, right? All of those factors and nothing else. It just has those factors. So if I look here, the factors of 20 are 2 squared and 5, and the factors of 21 are 3 and 7. So the LCM of 20 and 21 equals 2 squared times 3 times 5 times 7. Okay? Notice that that number is going to be divisible by 20 because it's got 2 squared times 5 as its factors. And it's also going to be divisible by 21 because it's got 3 and 7. So the LCM here is equal to 420. And that's the lowest one or the smallest one because it's the one that shares all of the factors or all of the prime factors of both 20 and 21 and nothing else. Okay? Shares all the factors of 20 and 21 and nothing else. So let's take a look at another example. Let's find the LCM of 24 and 36. Okay, so 24 is going to equal 2 squared, or actually 2 cubed, times 3. And 36 is going to equal 2 squared times 3 squared. Now, 24 and 36 are going to share some factors. Let's look at what they are when we separate them out. 2 times 2 times 2 times 3, okay? And then 2 times 2 times 3 times 3, okay? Now, what I want to notice is that, well, both of them share two 2's, okay? So I know I'm going to have that 2 times 2, right? And then I'm going to have that third 2, right? So that's the first three factors of 24. And then we notice that those 2 are also included inside of 36. So I don't want to add anything more, right? They're already there. They're already included, all right? And then I'm going to see, okay, I've got 1 3 in 24, okay? But then in 36, I've got a second 3, so I need to add that to it. So my LCM of 24 and 36 is going to end up equaling 2 times 2 times 2 times 3 times 3, okay? So notice 2 times 2 times 2, there's the 8, times the 3, that's 24, and then this 2 times 2 is 4, times the 9, that's 36. So this number right here incorporates both 24 and 36 in it. So it's going to be a multiple of 24 and 36. Okay, and it is 72. And since there are no additional factors, it's the least common multiple. All right, so this finishes up this particular lecture that introduces primes and introduces the greatest common divisors, factorizations, and the least common multiple. What we're going to look at next is we're going to be looking at something called the Euclidean algorithm, which is something that gets used in order to find the greatest common divisor. In addition to that, we're going to be looking at these things called linear combinations, which will also incorporate the greatest common divisor, right? And then we're going to use quite a bit more when we work into number theory. All right, so that finishes up this discussion.